Hello! In this video, we're going to explore a beautiful property of shapes called cyclic quadrilaterals. Our main goal today is to prove a very important theorem about these quadrilaterals. By the end of this lesson, you will be able to prove that opposite angles in a cyclic quadrilateral are supplementary. Supplementary, as you may recall, means they add up to 180 degrees. Let's first define what a cyclic quadrilateral is. A cyclic quadrilateral is a four-sided shape where all four of its vertices lie on the circumference of a single circle. Here's an example. Notice how the points A, B, C, and D are all on the circle's edge. This makes ABCD a cyclic quadrilateral. Now, the theorem we're going to prove today states that the opposite angles in this kind of shape are supplementary. This means that the sum of angle A and its opposite angle C is 180 degrees, and the sum of angle B and its opposite angle D is also 180 degrees. So, we've defined our terms and stated our objective. Now, let's get into the proof. The key to proving this theorem lies in another fundamental theorem from geometry, the relationship between central angles and inscribed angles. Let's state this theorem clearly. The measure of a central angle is double the measure of an inscribed angle that subtends the same arc. Let's break that down. First, what's a central angle? A central angle is an angle whose vertex is at the center of the circle, like angle AOC here. The arc it cuts off on the circle is arc AC. Next, what's an inscribed angle? An inscribed angle is an angle whose vertex is on the circumference of the circle, and its sides are chords of the circle. Here, angle ABC is an inscribed angle, and it also cuts off arc AC. This arc is the subtended arc. The theorem tells us there's a specific relationship between these two angles, because they both see the same arc, AC. It states that the measure of the central angle, angle AOC, is twice the measure of the inscribed angle, angle ABC. This simple relationship is the cornerstone of our proof. This means a central angle is always twice the size of any inscribed angle that shares its arc. Hold on to this idea. It's what we'll use to connect the angles inside our cyclic quadrilateral. Now that we have our tool, the central angle theorem, let's return to our cyclic quadrilateral and apply it. We'll use our quadrilateral ABCD. Let's start with one pair of opposite angles. Focus on angle B. This is an inscribed angle subtended by the major arc ADC. The central angle that subtends this same arc is the reflex angle ADC. Wait, I made a mistake. The central angle subtended by major arc ADC is the reflex angle AOC. Let's correct that. The inscribed angle B is subtended by the major arc ADC. The central angle for this arc is the reflex angle AOC. It's the big angle theorem. The measure of the reflex angle AOC is twice the measure of angle B. Now let's consider the other opposite angle, angle D. Angle D is also an inscribed angle, but it subtends the minor arc ABC. The central angle for this arc is the minor angle AOC. Applying the theorem again, the measure of the minor angle AOC is twice the measure of angle D. So now we have two equations. One relates the reflex angle AOC to angle B, and the other relates the minor angle AOC to angle D. These two equations hold the key to our proof. We're in the final stretch. Let's put everything together to prove our theorem. Let's start by recalling the two equations we just derived. First, the reflex angle AOC is twice angle B. Second, the minor angle AOC is twice angle D. Now, think about the two angles AOC, the minor one and the reflex one. They are supplementary. Together they form a complete circle around the center point O. The sum of the angles around a point is 360 degrees. Therefore, the reflex angle AOC plus the minor angle AOC equals 360 degrees. Now, we can substitute our previous findings into this equation. This is where the magic happens. We know the reflex angle AOC is 2 times angle B, and the minor angle AOC is 2 times angle D. Let's substitute those into our 360-degree equation. Look at that! We have an equation with only angles B and D. Let's simplify. We can factor out the 2, giving us 2 times the quantity of angle B plus angle D equals 360 degrees. Finally, we divide both sides by 2 to isolate the sum of the angles. This gives us the measure of angle B plus the measure of angle D equals 180 degrees. And there you have it. We have successfully proven that opposite angles B and D are supplementary. We could use the exact same logic with angles A and C to to show that their sum is also 180 degrees. The proof for the other pair is identical. Let's quickly recap what we've accomplished and what you should now be able to do. Our goal was to prove the theorem about cyclic quadrilaterals. To do this, we used the central angle theorem, which states that a central angle is twice an inscribed angle that subtends the same arc. We applied this theorem to our quadrilateral, relating the two pairs of opposite angles to the central angles at the center of the circle. By doing this, we connected the opposite angles. Because the two central angles around point O add up to 360 degrees, we were able to deduce that the two opposite inscribed angles, angle B and angle D, must add up to 180 degrees. So, you are now able to formally prove that opposite angles in a cyclic quadrilateral are supplementary using the central angle theorem. This is a powerful result with many applications in geometry problems. Understanding the proof gives you a deeper insight into the relationships between angles and arcs in a circle. Thank you for watching.